Hello everyone and welcome to this presentation about how to efficiently calibrate or tune e-motor and inverter, which we in AVL call the Advanced E-Drive Calibration. My name is Veronica and I am project manager in AVL. I have a PhD in technical physics and directly after university I joined AVL as a simulation engineer in the field of batteries. And today I am project manager in the integrated and open development platform in AVL, and I am caring for development process innovation with a strong focus on electrification. And one of the topics that I'm driving together with a lot of colleagues in AVL is the Advanced E-Drive Calibration, and I'm really happy to share this content today. Now, this is today's agenda, so I would like to start with giving you a bit of an historical insight into the evolution of powertrain calibration and why is it actually so challenging, more and more challenging, to calibrate powertrains and vehicles. Then I would like to show you what AVL can do in terms of e-motor and inverter development, testing and simulation. Then we will have a look at the Advanced E-Drive testbed. You will see that this consists of hardware aided by automation and simulation. It's a really nice tool chain that uses active design of experiment directly on the testbed. Then I would like to give you some insight into some of the use cases for E-Drive calibration and finally benefits and key message for you. So let's start with the evolution of powertrain calibration. So we can start in the year of 1995. We see that we have around 500 calibration parameters, we have one engine, we have one vehicle, and all of this can be more or less handled by one calibration engineer. Now let's jump into 2005. We see that we already have a lot more calibration parameters. We have more than one engine, we have a lot more vehicle types, and also some more people are involved. At the same time, we have a shorter time to market. If we look into 2015, of course, electrification business is added to this field. So while having more and more calibration parameters, more and more components and vehicle types, we also have more people from different teams with different backgrounds that need to talk to each other, again, shorter time to market. And you see where this is going. This will become more and more also considering ADAS functionalities and so on. So what is needed is really new approaches to achieve cost, time, and quality targets. And I want to today to present you on the example of E-Drive calibration, how we in AVL are using automation, simulation on the testbed, as well as front loading to tackle these problems. One of the challenges that our customers are facing today is choosing the right testing or development environment for different development tasks at the right time. So these testing environments can range from simulation to virtual testbed to E-Drive testbed, integration, powertrain, chassis dyno testbed, up to road testing. And you can see here now an indicative distribution of the development effort of lots of our customers today. So as you can see, a lot of development effort is actually done in very late stages of the development process using real components and real prototype vehicles. Our aim at AVL and also for a lot of our customers is actually to front load these development tasks. What does it mean? It means that you shift the efforts that you have in very late stages of the development process to earlier stages, using simulation on the testbed, using automation, using data management, and so on. And overall, this means that you can reduce development and testing time by making decisions earlier. You can reduce cost by shifting your development tasks to earlier stages. And in a lot of cases, you can increase quality because you increase your know-how earlier. Now let's have a look about what AVL can do in terms of e-motor, inverter development, testing, and simulation. So, you know, AVL is distributed in 3 business units: engineering, testing devices, and software tools. And here you can see an overview of all the E-Drive activities that we have. So AVL is actually involved from concept to start of production. So we do, of course, as I want to show you today, testing, benchmarking, E-Drive characterization. We do a lot of simulation, which means thermal, mechanical, electric simulation of e-motor and inverter. We're also doing inverter and MCU development, so controls. Together with our customers, we're developing and building prototypes. We do system validation and finally also turnkey lab solutions. So what is actually calibration of e-motor and inverter? Calibration is nothing else than tuning parameters, tuning lots of parameters. The overall goal of tuning, calibrating e-motor and inverter is increase the efficiency, which means we want to have as little energy as possible from the battery. We want to optimize efficiency, drivability, performance, durability, and also, for example, considering NVH topics. So if we break this coming from a vehicle level into the powertrain components and down to e-motor inverter, we see that we have different development tasks. Now we're in calibration. We can subdivide this calibration into different work packages, and then these calibration tasks within these work packages are the ones that we want to address with this advanced E-Drive calibration toolchain that I want to show you today. So to summarize a little bit for now, what is the challenge in e-motor and inverter calibration? So the goal is really, it is essential to optimize or to maximize the electric range of the vehicles. E-Drive calibration means a multi-parameter optimization, while at the same time respecting different limits. Currently, at our customer, what we see is that sometimes there is a rough pre-calibration and simulation, and very often there is lots of manual, iterative calibration loops on the testbed, which actually means it's hundreds of hours on the testbed and a lot of repetitive work. So what we actually being asked from customers is, how can I increase the efficiency on my testbed? How can I reduce manpower? And also, how can I get the best quality in minimum time? And so this is exactly what we want to address with this toolchain. So AVL provides a methodology and a toolchain to efficiently calibrate e-motor and inverter. And at the same time, I want to mention that we're doing a lot of consulting and workshops really to enhance the efficiency of the E-Drive development of our customers. So now let's have a look at the advanced E-Drive testbed. So here you see how a typical E-Drive testbed looks like. Of course, the units under tests are the inverter and the e-motor. Then, of course, we need the battery emulator for getting voltage and power supply. We have the ECU and also power measurements and the dyno. So this is like the hardware of our E-Drive testbed. And now we see what turns this E-Drive testbed into an advanced one. So we do this step by step. First of all, we add an automation system. So testbed automation system that is responsible for automation, for control, as well as for data storage. Second step is a very powerful power measurement, high frequency power measurement and data acquisition system. Of course, we need a communication to control unit. And also, what is very powerful in this toolchain is an optimization tool, a model-based calibration that uses active design of experiments directly included in the testbed. And finally, to analyze results, to do data processing, KPI calculation, report generation, we have integrated the data processing tool. So this is how the toolchain overall looks like. The hardware is aided by automation as well as optimization and makes this calibration very efficient. I want to also say some words about this design of experiment on the testbed. So there are two types of design of experiment, traditional one as well as active design of experiment. In a traditional design of experiment, what you're doing is you're starting with a full test matrix generation before you go to the testbed. Then you go to the testbed, you do all the testing, and finally a model is generated. Then on an offline mode, in a simulation, you choose your optimization criteria and you're trying to find the optimum. Sometimes this fails because you did not test in the right regions. So this is why in some cases active design of experiment can help a lot. So the workflow for active design of experiment looks like this. You start with a start matrix generation. You already choose the target results that you're interested in, and then you go to the testbed, and in iterative loops you are recreating models. And actually the model will finally tell you that you've tested enough. And then you end up with final model creation, and also the optimization is successful. So this active design of experiment, also in case of E-Drive calibration on the testbed, is a really powerful routine to save a lot of time and increase your quality. After having a look at our development environment, we want now to have a look at which kind of use cases we can address with this toolchain. So here you can see like an indicative effort distribution of the different work packages that we in AVL see for the E-Drive calibration. It's 4 work packages: base calibration, drivability, thermal strategy, and diagnostics. And you can see also the indicative effort that we in AVL, based on our experience, see for these tasks. Of course, we understand and we are aware that this can be different from customer to customer, but still it's a nice clustering of the work packages. And these big work packages can then be, moreover, broken down into smaller ones. As you can see here, the base calibration, for example, ranges from calibration of motor parameters to calibration of current controls and so on. So you see here for each individual calibration tasks how much effort is needed to do that. And I would like to give you a little bit more insight into these 3 calibration tasks. So calibration of motor parameters, calibration of current controllers, as well as for the thermal strategy, calibration of derating. So this is some of the use cases that we already covered with our toolchain on the testbed using automation and optimization. This is the overview of these 3 use cases. You see which design variables, which kind of limits we need to respect, and also which kind of results or exemplary results we're receiving in the end. And let's have a closer look into this base calibration. So the design variables are, of course, the theta angle and the current amplitude. The limits that we need to respect are the back EMF and temperatures, rotor temperatures, stator temperatures. And finally, as a result, using active design of experiment, we can very efficiently receive these optimized surface maps. So based on this use case, I would actually want to a little bit walk you through what is the challenge and what is the steps that we're doing in our toolchain to increase the efficiency. So base calibration means we want to maximize efficiency of inverter and motor for all speed load conditions. What is the challenge in this? It means we need to loop for each motor version, controls update, DC voltage, for each temperature, for each speed, and so on. We need to adjust until we get the maximum producible torque. So we have a high amount of variation parameters. We have to respect physical limits at the same time, and we end up in a multidimensional calibration. If we do this by hand, it means a lot of time for iterative loops, a lot of time for this manual approach. So in our toolchain, step 1 would be automation. Now we're adding testbed automation system for replacing this repetitive work. We still need to loop for each of these different motor version, controls update, and so on. But this repetitive work that would be done by an engineer on the testbed can be replaced by the automation system. What does it mean overall? We're reducing manpower. The second step is the optimization. So we're using active design of experiment besides the testbed automation. We're using this model-based calibration in order to actually avoid looping through all of these different motor versions, controls, update, and so on. So we let the model decide what to test. And finally, this will mean, besides reducing manpower, we're enormously reducing the testing time, and at the same time, we're increasing the quality because we're testing in regions that maybe from a pure manual approach we wouldn't have done. Finally, I would like to summarize and share the benefits of this solution with you. So we were talking about the advanced E-Drive calibration. The challenge is to maximize the electric range of vehicles and optimize the calibration of e-motor and inverter. AVL has developed a methodology and a toolchain to do this in a very efficient way by accurate testing, calibration, and validation on the E-Drive testbed. We have proven benefits from several projects in terms of time, cost, and quality. Compared to a pure manual approach without any simulation, we can save up to 80% of the time in the calibration process. We have the benefit of a seamless toolchain integration on the testbed, which really assures a maximum testing efficiency. In terms of cost, we of course have a minimized UUT and testbed occupation time, a minimized measurement effort, and also a quantification of specific commercial benefits. In terms of quality, we have a high repeatability, a high traceability of the results, and finally, an optimized efficiency of the E-Drive, which increases the electric range. Now, so AVL is offering this toolchain and methodology to support calibration and validation throughout the whole development process. We're doing multiple projects already at customers worldwide in this field. Usually, we like to start out with an application workshops where we are bringing our engineers and our know-how together with yours in order to really figure out what is the most attractive development task for you in your specific development environment. We also offer proof of concept projects that are smaller ones to really demonstrate the efficiency of this toolchain, and finally also, of course, the toolchain implementation. Thank you very much for listening. I hope you enjoyed the content. If you want to get in contact with us, please just write me an email. If you have questions, if you want to have more details, or even are interested in a project, I'm really happy and I'm looking forward to getting in contact with you. Thanks for listening and goodbye. Ciao!